So, let us resume our lecture on role of nanomaterials in agriculture. So, we are into the animal production section, role of nanomaterials in animal production, and we will continue our story about cerium oxide nanomaterial, what we have been talking for a while now. So, I told you that this all started in University of Central Florida somewhere around, I would say 2003. This was the time when it all started. So, and it showed, first of all, it showed a radioprotective activity, it showed neuroprotective activity, especially for spinal cord repair, and this is where for the first time in this paper was highlighted the autocatalytic terminology for ceria was introduced, autocatalytic activity and autocatalytic action. The nomenclature for ceria as autocatalytic mechanism started here. Similarly, there was another paper with the cell lines of the neurons, came in BBRC, Biochemical Biophysical Research Communications. Then you have a JBC, Journal of Biological Chemistry, highlighting the work of Papuchin Kolarakuti, saying it has a cardioprotective role. Simultaneously, there was multiple studies, of course, by Jim Manganese and from Oklahoma Eye Center and Sudipto Seal, the joint work, which showed that it helps in recovery of the retinal neuron. So, simultaneously there was a couple of other work which showed cerium could be used as a drug delivery tool also. So, I am not getting into that part. What is important here is this material showed tremendous promise somewhere around this time, and now we will see tons of papers which have come in this area over last I would say almost 14 years time, and maybe some of these earlier studies people have almost forgotten that where it all started, and it was the same time. There was another very interesting study which came, if I remember it right, chemical communication, which said that cerium, and it came from a gentleman called William Self and Sudipto Seal. It's the joint work, came as cerium oxide nanoparticle mimics SOD activity. Now, if you remember SOD, we talked about SOD out here, superoxide dismutase activity. So, look at the interesting part, how studies evolve. So, out here for the first time there is, you have 1, 2, 3 what nature has given you. Now, your inorganics is giving you CeO2 or C2O3. A new enzyme or new autocatalytic molecule which is doing the same thing as these enzymes are doing. So, this tells us the bioinorganic origin of ours, the whole field of bioinorganic chemistry. A very interesting molecule which is purely inorganic, purely inorganic, finds applications in areas which exactly the naturally occurring enzyme system does. Simultaneously, there was another interesting area which was quantified, showed. So, around this study came around 2014, where, so now you are realizing that hydrogen peroxide molecules are getting scavenged. Okay? In other words, the free radical generated by hydrogen peroxides are getting scavenged. So, if you could do this titration right, then, so this is basically a titration which is happening. If you do it the correct titration, then you can use cerium as a probe for H2O2 detection and quantification in a system, because how many molecules of H2O2 is getting transformed. And if you really look at this reaction even much more carefully, depending on the number of electrons which are getting converted. So, in other words, what is happening? There is an oxidation and there is a reduction happening. So, if you use techniques like cyclic voltammetry, which are electrochemical technique, you can actually make a hydrogen peroxide sensor, hydrogen peroxide quantifying agent out there, and it could do this. And not only that, there are very interesting studies showing. I'll come to this sensor part first, and then I'll come to some of those interesting studies. This quantification of free radical using cerium oxide nanoparticle could be used. There are preliminary studies showing could be used now as a animal world, if we talk about, as a diagnostic tools for free radical sensing, okay, and quantification using cerium. A simple inorganic molecule, almost now, through this last 14 years of tremendous effort around the world, which all originated in University of Central Florida, is now took the central stage. There is another interesting study which showed that cerium helps in DNA repair, which was a big area. If you look at some of these molecular biology aspects we talk about, one second, yeah, out there, out here. So, the molecule has amazing power and it is fairly biocompatible, and the advantage with such molecule is that they are autocatalytic and they are needed in very small amount. Okay. So, among all this, let me add one more into this. They helps in DNA repair, and this could be used as sensor H2O2 sensor and we have already talked about their role in neurogenesis and all other things. But simultaneously, there is another aspect which was evolving. There are a couple of papers which came from Korea at that time saying that it has toxicity. So, this is one area which will always come across whenever we talk about nanomaterials. But what is interesting to note here is, I will take you back to some of those techniques what we taught you in the beginning. If I take you back, if you remember, when we talk about how we synthesize nanomaterial, in terms of its synthesis. I will come to the synthesis part. Different mode of synthesis, either you do a top down synthesis or you do a bottom up synthesis. So, whenever we do a top down synthesis, we use, as we talked about, we use ball milling, we use different kind of techniques. What happens is, when we are breaking down a big bulk molecule, these particles which are generated may have sharp edges. And this is very important for you to understand. These kind of sharp edges, when you are using in biological systems, any kind of biosystems, they may show inflammatory effect. So, something which otherwise is exceptionally useful for us may turn out to become a disaster because you synthesized it in a way that will not support the result. So, while these studies are coming up from University of Central Florida and the collaborators of James J. Hickman, Sudhit Tusil, Rajlinsky, Papachan Kolarakudi, Florida Hospital, Orlando Hospital Systems, Oklahoma Eye Center, a study from Salk and the West Coast in California, or I think it is from Scripps, not from Salk. The study on neuronal cell lines. There were two studies, if I remember it right, which came up from Korea saying that, they cause inflammation, and one needed to look at those papers without rejecting them. This is one bad thing you can do, you reject something. Oh no, this does, just because you are opposing me. Science, knowledge, understanding is not like that. You try to understand what does that mean. Upon looking, you will realize how the material is being synthesized, and that's why it is very important for you guys to understand, before allowing anything to get into the body, you should know how you are getting this material. It's very important. So, it was observed that much of these syntheses were top down or a very high temperature synthesis, which was followed for cerium, which is perfectly right, because cerium all throughout has been used. If you look at it, cerium all have been, so whenever we talked about cerium, I told you the cerium has all been used for rocket fuels, for catalysis, for automobile industry and all other sorts of things. And there was no point for it to be synthesized, because you needed a bulk quantity, and nanocerium was synthesized under those kind of harsh conditions. So, what was obtained from those, if you use those cerium, they may not be able to show you the kind of amazing beneficial property you see. Not that they lose their property, because those particles have very sharp edges. Those particles are not really spherical, not really so uniform, and that is possibly one of the reason why many of these studies which were being conducted showed contradictory results. It is not that result was wrong, it was material was different, same material, but how you are synthesizing. That was one of the critical reason why I took in the initial phase of the course that much effort to make you understand that why these kind of synthesis protocol, the chemical synthesis, physical synthesis, mechanical pressure, high energy radiation, thermal energy, and where all these things are moving. So, one of the thing, what if you remember, I highlighted very clearly, we have to emulate nature, how we are synthesizing, and I'll highlight one of the synthesis techniques in possibly my next class, where I'll show that initial cerium synthesis were done, which showed the biological activity, were done in a very different way. And as a matter of fact, that's what people have been following since then. They use the sol gel, reverse micelle methods, microemulsion techniques and all those. None of them use any of these techniques. They use very simple, gentle techniques, something like this, okay. And much of the efforts are currently on these kind of techniques, which are more biologically based techniques, which are much more easy technique, much more, of course, they may not be a very bulk production unit, but who needed a bulk production unit? You could have small production units and they will be synthesizing at lower temperature. So, what is the temperature? What you are using? What is the pressure you are using? So, this is the reason one has to look at every study very carefully without getting biased that, you know, this result doesn't fit in my storyline. It means it's a bad result? No, it may not be a bad result. It may be something which you are missing out completely. So, while talking about, so again revisiting all our very first week lectures, not even to come back to the real time now. So, while cerium was gaining significance in these areas of neuroprotection, cardioprotection, radioprotection, photoreceptor repair, H2O2 sensor, SOD mimetic, DNA repair, there are studies in literature which will contradict some of these. Do not get bogged down and do not disrespect those people. They have reasons because they synthesized it in a very different way and slowly, because whenever a field unfurls, when I am offering this course, you know, 2-3 years down the line, this will be even much more broader. I mean, 20 years down the line, probably people will not even bother. This is all outdated. So, but what is important for us is to realize how we are getting that material, how this has come to us. So, much of these work which was concentrated in one part geographical location, much of these synthesis which were being done was low temperature synthesis, absolutely no ambient pressure, sorry to put it precisely, ambient pressure, absolutely no harsh conditions, okay. So, some of these things were being maintained there in order to ensure that these particles what we obtain have a very smooth geometry like this, and this geometry is extremely important, that they should not have something like, you know, sharp edges like this or something like this. And being a low temperature means it is a low energy synthesis. It needs much lesser energy. Of course, in that whole process your production will be slightly lesser, but you are spending less energy, you know, it always compensates for it, okay. So, having said this, in the next class I will move on to one of the synthesis techniques, and then I will move on to where they may find applications from the laboratory studies, laboratory trials into the line of animal production. Okay? Thank you.